Hi, I'm Lewis Quayle, data scientist, bioinformatician and maintainer of lewisdoesdata.com, which is my website where I blog data science tutorials and guided data analyses. Today I'm going to be taking a look at how to run bulk RNA sequencing or RNA-Seq data processing on a high-performance computing cluster, which is a step that's usually not included in most RNA-Seq tutorials. This video is going to serve as a step-by-step guide for how to carry out the various stages of setting up and running an RNA-Seq data processing pipeline on a high-performance computing cluster or HPC, as most people won't have access to the kind of local compute, such as a high-end PC or laptop, that would be needed to run this pipeline on the dataset that we're going to be using. The pipeline that we're going to be using is the fantastic peer-reviewed NF-core RNA-Seq pipeline. I'm going to show how to run this in star arson mode, which is probably the most comprehensive pipeline configuration, which uses the fantastic star aligner written by Alex Dobin and the arson transcript quantification tool. I've included a load more background information and links to all the sites and tools that I mentioned in the companion blog post on my website, and I'll include a link to this in the description below. You'll also find links to the template versions of the scripts that I'm going to use here on the blog post, so check it out if you want to save yourself a bit of time following along. So the first thing that we're going to need to spend some time doing is making sure that we've the software required to run these pipelines installed. In short, we're going to need some sort of containerization tool, i.e. Docker, Singularity or Aptainer, as well as Nextflow and NF-core installed. Now, given the breadth of high-performance compute infrastructure and workflow managers and the specific ways that these systems might have been configured across research institutions, providing a tutorial on how to undertake the setup process for each different scenario would be almost impossible. So what I'm going to say is that if you're using a HPC, the likelihood is that somebody will have already installed Docker, Singularity or Aptainer on your system, and if not, you'll be able to get your system admins to do this for you. You'll also need to either have Anaconda or Miniconda installed as a software module on your system, or follow a setup guide like the one linked in the companion blog post for how to make Miniconda available as a personal TCL module. Everything else, including Nextflow, NF-core and all of their dependencies, can be taken care of using a Conda environment, which makes getting set up and running really easy, and which is why I recommend this particular approach. Once you've made sure that Conda's installed on your system and your channel priorities configured, i.e. set up to use BioConda and Conda Forge, the next thing to do is create a Conda environment into which we can install Nextflow and NF-core and all the requisite dependencies. So I've made sure that I'm logged into the HPC that I've got access to here, and I've requested an interactive session with 4 GB of RAM, which would be more than enough for what I need to do. So the first thing that I'm going to do is load my Conda module by saying module load miniconda. And now we're going to create our Conda environment by saying conda create. And we're going to call the environment nfenv and we're going to install into that Nextflow and NF-core. Once you've followed all the prompts and your environment's set up and you receive an output to the screen similar to the one shown here, the next thing that you can do is activate the Conda environment that we've just created. Now, certain systems will allow you to say Conda activate and then the name of your environment. On the HPC that I use, it requires you to say source activate and then the name of the environment. So we can see from our prompt now that the NFenv environment is active. So the next thing to do is test that Nextflow is installed in this environment and working. So we can check that Nextflow is installed just by saying Nextflow info. So now we can run a simple hello world pipeline to check Nextflow and the containerization software are working correctly. So we can say Nextflow run hello. So now that we're happy that everything's set up and working, we can say conda deactivate to actually deactivate our environment. And because we won't be needing the module loaded at the moment, we can say module unload, and then in this case, miniconda. So now that our Conda environment's created and we've checked that it's working, we can move on to set up our project folders. So this is a somewhat opinionated guide, i.e. it follows the system that I've developed. So we're going to use the same project directory hierarchy that I use for almost all of my projects. And to set this up, we can run a simple one-line bash command similar to those that you might have seen me run in previous tutorials. So I've already navigated to my user directory in the file system where I want to create my project folder. So I'm just going to run the make directory command and I'm going to say today's date and then an intuitive name for the project, so RNA-Seq end-to-end. And once we've done that, we can use some brace expansion in order to set up our nested directory tree structure. So I've just time-lapsed out me typing in that command. So once you're happy that you've set up the command with the brace expansion as shown here, you can hit enter. So now if we just use the ls function and we point that to the folder that we've just set up, we can see that we've created a nested directory tree where we've got 3 folders within our project top level called data, results and source. Within the data folder, there's folders for reference, raw, reference and sample sheet. All of those are empty. The results folder is also empty. The source folder contains 3 other directories called nfconfig, nfparams and shell, all of which are empty. So that was nice and easy, and now we're ready to get the data that we're going to use for this tutorial. The data set that we're going to use for this tutorial comes from the publication Induction of Fibroblasts Senescence Generates a Non-Fibrogenic Myofibroblast Phenotype that Differentially Impacts on Cancer Prognosis, and is a data set consisting of 3 independent samples for 3 different cultures of human fibroblast cells that are either untreated, TGF-beta treated, or irradiated. So I've put a link to this project repository page shown here in the companion blog post. So if you visit this, you can see a detailed description of the samples, as well as get hold of the metadata file, but there's also a direct download link for that in the blog post. So the easiest way to download all of the fastq files that we're going to need at once is using a small shell script, such as one that I've already preloaded into my shell folder. So I'm just going to change into the project directory that we've just created, and then I'm going to say less source shell, and then we're going to look at the shell script that I've already created. So you can see that the script's relatively simple. It contains the normal bash bang line, and then I've created a raw dir variable which points at the raw data subdirectory within our project top level that we've just created, and then I've created a links variable which has all of the links to the files that we want to download, and then I've created a really small for loop that's going to use the webget function in order to download each of those sequentially. So you can download a copy of the template for this from the blog post and then modify the file path according to your file system. So once we've done that, we can just run the bash command and point that at the file that we've just looked at and hit run, and it'll start to download each of the fastq files. That's going to take a little while to run, so I'm going to time lapse that out and I'll be back at the next step. So now we're back in our terminal. We can look at the script that I've already made for downloading the reference genome. So you can see that similar to last time, we've got the bang line at the top. I've created the variable that points to the reference directory within the data subdirectory of our project top level. And then I've created another variable called version. Because the version changes regularly, that means you'll be able to update this script if it's a newer version or an older version you want to use, and everything else can remain the same. So then I've got 2 separate webget calls that will download the FASTA file and the GTF file, and then I've got 2 separate calls to the gzip function that will allow us to decompress those gzipped archives. So as before, if we quit out of that and we call the bash command on that file that we've just seen, that will download the reference genomes to the reference directory within the data subfolder of our project. Okay, so after that's run, the last thing that we need to do in preparation is to set up a sample sheet for the files. Now, don't confuse that with the experimental sample sheet that I spoke about being housed on the European Nucleotide Archive that describes the actual experiment. This is the one that NF-core requires to understand which files we want to analyse, how many lanes the samples have been run across, whether we've got paired or single-end reads, and what the library prep protocol was. So there's a detailed guide on how to do this for most NF core pipelines, and that can be found on the pipeline documentation pages under the usage tab. So again, I'll put links to that in the blog post. So I've set up a sample sheet for this project a little bit ahead of time, so we can just view that quickly as previously. So you can see that in our case, we've got one file containing single end reads for each sample, and the sample sheet layout's relatively simple and only requires the sample name, which is in the sample column, the full path to each of the respective files, and the strandedness all on the same line because we've got a single file for single end reads. The fastq2 column in this case is left blank, and then the strandedness is set to reverse, and I found out those details for the library prep protocol based on the information contained in the experimental metadata on the ENA project site. So a template version of the sample sheet shown here can be downloaded directly from the blog post too. Great, so now we've got all of the required files, we can actually go and configure the NF Core pipeline run using the pipeline launcher tool on the pipeline top level page for the RNA-Seq pipeline. So once you land on the NF Core homepage, if you go to pipelines and then in the search bar type RNA-Seq, you'll see that over here the RNA-Seq pipeline is shown. So if we click on that, that takes us to the pipeline top level page where hopefully you'll be able to see this launch version button. So if we click the launch version button, you'll land on this pipeline launcher page where it allows us to configure all of the Nextflow command line flags. Now, I've already been through and configured this so that I can show you the key fields that I usually focus on. So as we're scrolling down, we can see that I've inputted the Nextflow profile, the NF Core profile that I use for the high performance computing cluster that I have access to. If you don't have an institutional NF Core configuration available, don't panic. There are a couple of extra steps that you need to undertake to create a custom configuration, which are shown in the linked blog post. Now, when we move down, we can see that I've set up the work directory, which is the directory which intermediate files will be written to. Now, I always recommend that when I'm inputting the paths into the configuration tool, that you use the absolute path rather than the relative path. So you'll see that I'm always including the root of the file system as well as the absolute path to the project top level and then all of the subsequent directories in there. I also set resume to true, which means that if the pipeline does fail for whatever reason, it'll resume from the most recent cached point. So as we're scrolling down, we can see that there are mandatory fields highlighted by red asterisks. So the input field requires you to put in the path to the NF sample sheet CSV that we set up. And also we're required to specify an output folder. So I always set this to results and then NF output. You can also optionally put in an email address so that if when the pipeline starts and when it finishes, you'll get an email notification. Then as we're scrolling down, we can see that we have to put the absolute path to the FASTA file that we downloaded within the reference folder and the GTF annotation that we downloaded within the reference folder. The next field that I make sure that I edit is to change, if it's set to fastq, I change the trimmer to trim galore because I just prefer this tool. And then when you get to the alignment options, we need to make sure that we change the aligner to star awesome. We can leave the rest of these fields set to the defaults. Now, when we get to the optional outputs, there are a couple that I recommend changing from false to true, which are the save reference and save trim options. And then finally, once we get to the option for process skipping, the only one that I recommend changing to true that isn't already set to true is this skip dseq2 PCA and heat map plotting, because we're going to be doing that in later parts of the tutorial anyway. When you reach the bottom of the page, you'll see that there's a launch workflow button. When you're happy that you've inputted all of the requisite fields, you can hit launch workflow. And after a short while, you'll be taken to a page where you can see that it's created for us the various NF core parameters that we configured. And it's also created for us a Nextflow run command, which we can paste into a shell script that we can use to create and run our driver job for the entire pipeline. So now that we're back in our bash terminal, we can just use the NanoText Editor to say source nf params nf-core nanotext.json. And you can see that I've already created this file and pasted in all of the information contained within that first box on the launcher page site. So then if we hit Control and O to write the file out, hit Return, and then Control and X to exit the NanoText Editor. Back on the launcher site, the next thing that you can do is to copy this entire line here, which is our run command. And then back in our bash terminal, you can follow a similar process to create within the shell directory a shell script called nfrun.sh. So I've pre-configured the nfrun shell script to include some additional information as well as the run command that we've just copied. Now what you'll need to do is make sure that you incorporate the system-specific scheduler flags required by your HPC, and probably the most important one here is to request the Java virtual machine which runs the driver job has to have at least 3 GB of RAM, and then down here we make sure that we limit it to between 1 and 2 GB of RAM, which means that if the driver job requests a spike in RAM, that we're not going to cause the pipeline driver job to fail because of excess resource requests. Now the other lines that I've included here are lines to load the miniconda module and activate the NF environment that we created within the driver job Java virtual machine, as well as also exporting the path to our Singularity or @tainer cache directory. And then I've also set up a couple of variables which mean I can point to the project top level and then some of the critical subdirectories within that. Then finally at the very bottom, I've pasted in the run command that we copied from the NF Core launcher page, and I've broken that up over multiple lines just so that it's easier to see what we've got that make up that run command. So you can see that we've got the Nextflow run command, and we're saying run the NF Core RNA-Seq pipeline. This R flag here asks to run the most recent version 3.14.0, and then we've got the profile flag, which in this case is the institutional configuration that I set up for the HPC that I have access to. But if you don't have an institutional configuration, just set that to the name of the containerization tool that you're using, and then follow the steps in the linked blog post to incorporate a custom configuration, and everything will work fine. Then our penultimate flag is the path to our working directory, which we've specified up here. And then the final flag that we have is the path to the nfparams.json file that we've just created. So once you've done setting up your driver job shell script, we can hit Control and O, write the file out by hitting Return, and then hit Control and X. So the very last thing to do is just to submit our shell script as a batch job. So I'm using Slurm, so I'm going to say sbatch, and then I'm going to point it to the source folder and the nfrun shell script that we've just created. After a couple of minutes, if you've submitted that batch job from within the project top level directory, you'll be able to say less nextflow.log, and you'll be able to view the log file which is tracking the progress of the pipeline, where you can see various parameters that we've inputted. Now if you hit Shift and G, it'll take you to the bottom of that log file, and you can see that some of these processes in the pipeline have started to be deployed to the worker nodes. So I'm happy that everything's running as it should be. Then you can hit Q to exit, and you can leave the pipeline to run. Once you're happy that the pipeline's running, it's time to go and make a cup of tea, because it's going to take a couple of hours or so to run on a decent system and a bit longer on a less beefy HPC. The last time I ran this pipeline on this data set, it took about 2.5 hours. So I think that's where we'll leave this video for today. There are a few extra steps in the linked blog post for how to download what I think are the essential files into the local full project directory tree that we're going to create next time to start working on our downstream analyses. So thanks for watching. I hope you enjoyed the video. If you did, please do consider subscribing to my channel. Good luck with your RNA-Seq data analyses, and I'll catch you next time.